All right, we're going to take a look at a couple of examples for solving using Cramer's rule, solving a system of equations using Cramer's rule. This is one application of a determinant of a matrix. So just a little reminder here, Cramer's rule is x would be determinant with respect to x over d. Y would be determinant with respect to y over d. And if we were solving for z, determinant with respect to z over d, whatever variable we're solving for, I just wrote it in terms of x and y because that's what I've got in this 2x2 system here, two equations, two unknowns. The determinant, what we call the base determinant, cannot be zero. Right? If the base determinant was zero, that doesn't mean there's no solution to the system. It just means that we cannot use Cramer's rule. Right? The reason would be simply that would put a zero in this denominator, which would give us two undefined amounts. So that being said, I always want to find that base determinant first, and that would mean with the variable columns. So D, in this case, would be my 2x2 square matrix with the x column coefficients, 5 and -1, and then the y column coefficients, -2 and -3. Always check when we write these down. We want to make sure that we have the right values. We're not missing a negative or anything. I've got 5, -1, -2, -3. And we'll get some review here on actually working out a 2x2 determinant. So 5 times -3 minus -2 times -1. Always think of it as going down this way, minus coming back the other way. All right, if I evaluate this, let's see, that would be -15 minus 2, -17, not 0, so we're good to keep going. We want to finish up, figure out what d with respect to x is, d with respect to y is, and then we can get what our x and y values would be. That would be the solution of this system. D with respect to x. What this means is our answers replace the x column. So -10, 19, and replacing that x column. The y column does not change, still -2, -3. Evaluate this 2x2. Determinant, -10 times -3 minus -2 times 19. And let's see there. That would give me, let's see, 30 minus -38 would be a 68. And now we'll go for d sub y. So what this means is now our answers to each equation, -10 and 19, are now replacing the y column. And the x column will stay the original, 5, -1. So then we would have 5 times 19 minus -10 times -1. And so 85. So we have our values for D, our base determinant, being -16, our value for D sub x, determinant with respect to x being 68, and the value of D with respect to y, which would be 85. Now we can finish out solving this problem. X be the d with respect to x value over d. So in this case would be 68 over negative 17. And that's a negative 4. Y would be 85 over negative 17, which would be negative 5. So the solution to my system here of equations, this two equation, two unknown system, is the ordered pair negative 4, negative 5, or we could say x equals negative 4, y equals negative 5. Typically, we'll see it written as an ordered pair, but it's also fine to say x equals negative 4, y equals negative 5. Those would be the x and y values that will solve that system. Or this is a linear system. If I were to graph these two lines on a plane, this would be where the two lines would intersect at that point, negative 4, negative 5. All right, now we're going to take a look at Cramer's rule still with a 3x3 system. So 3 equations, 3 unknowns. So let me change the set of equations that are up here. All right, this time I've got a 3x3 system, 3 equations, 3 unknowns. And I changed the directions a little bit. Instead of solving the entire system, I said, use Cramer's rule to solve for z only. So we're just going to solve for the variable z. The only real downfall with Cramer's rule is when you're working it all out by hand, the determinants, especially when they're 3x3 determinants, and then if we get much larger ones, say in a different course much later on, 4x4, 5x5, it just takes a while to just grind those values out by hand. So this will give us some practice working out a 3x3 determinant, but by saying just solve for z, we'll need to find just 2 of them, because what we want to remember is z would be d with respect to z over d. So we would have to find the base determinant d, and then d with respect to z. Okay, so let's go for that base determinant first. Again, I typically go with it first just because I need to remember it cannot be 0. And it's not very often or very common that we do get a 0, but I'd sure like to know if it was 0 and I couldn't do this before I went through the d with subscript of z. So a base determinant, remember, x column, y column, z column. Got those values there. So now let's review evaluating a 3x3 determinant. The first thing I want to do is rewrite the first 2 columns. So 3, 4, 5, negative 2, negative 3, 2. Okay. And then we're going to go diagonally this way. So we're going down, plus down, plus down, minus, coming back, minus coming back, minus coming back. Right, so I'm looking for my 3 elements. So I'm going to start with that 3, and there's my 3 elements going down. 3, negative 3, 1, plus, there's my next 3, negative 2, 5, plus, there's my next 3, negative 2, 4, 2. And thus, these 3 parts, I'm not worried about going forward because there's no other element there. I don't have 3 elements, I've just got 2. So we're looking at the lines or the diagonals with the 3 elements. There's one of them. 3, negative 3, 1. Second one, negative 2, 5. Third one, negative 2, 4, 2. I'll write those down. So that would give me 3 times negative 3 times 1 plus negative 2 times negative 2 times 5 plus negative 2 times 4 times 2. Diagonally down. Minus coming back the other way. Okay, so first thing I'm going to do, We'll start with this right side. There's that negative 2, 4, 1. Then 3, negative 2, 2. Then negative 2, negative 3, 5. So again, start with that top right. Negative 2, 4, 1. Then 3, negative 2, 2. And then negative 2, negative 3, 5. And again, each one subtraction. So minus negative 2, 4, 1. Minus 3, negative 2, 2. And then minus negative 2, negative 3, 5. And then we need to evaluate this. Combine all of these terms. Let's see here. We would have a negative 9 plus be a 20 plus negative 16 minus negative 8 minus negative 12 and minus 30. Unless I made a mistake there, which when you get all of these different calculations, it is certainly not uncommon to make a careless error doing our evaluations. All right, all that together gives me negative 15. So there is that base determinant B value. And being the fact that I've got a small board here, I'm going to erase this and then work on D subscript Z, D with respect to Z. But I know this D value is negative 15. So I'm just going to go ahead and put negative 15 in that denominator there. That'll help me remember the value that I got. And now I'm going to go find D with respect to Z. And as you saw with that part, some of the worst parts of dealing with a 3x3 is just simply all of the calculations. It takes quite a bit. So D with respect to Z, what we want to remember is that means that the answers to each of the linear equations replace the Z column. So negative 11, negative 5, 82, all in the Z column. X column's the same original, Y column's the same original. And then we're ready to evaluate. So again, I rewrite the first two columns. And then I'm ready to go. Just to kind of review again. We're going to go down, plus down, plus down. So I'll start on that top left. There's that positive 3, negative 382, negative 2, negative 5, 5, negative 11, 4, and 2. Get those down. You're going to have 3 times negative 3 times 82 plus negative 2 times negative 5 times 5 plus negative 11 times 4 times 2. And now we're going to minus. So minus coming back 3 times. So we'll start on that top right. Coming back, there's my negative 2, 4, 82. Then 3, negative 5, 2. And negative 11, negative 3, 5. So minus negative 2 times 4 times 82 minus 3 times negative 5 times 2 minus, I'm at the negative 11. Negative 11 times negative 3 times 5. We'll finish up this evaluation. Get some larger numbers in this one. So let's see, that's negative 738 plus 50 plus negative 88 minus negative 656 minus negative 30 and minus 165. All right, let's get those combined. Gave me, again, unless I made a careless error somewhere, I've got negative 255. Oh, there's that D with respect to Z. Negative 255 divided by negative 15 is 17. So there's the value of Z. Okay. Now again, I don't know what X and Y is in this particular case because I didn't solve for either one of those, but I did find Z. If I wanted to say find X instead of Z, I just want to remember I would have still found that base determinant first and gotten negative 15. If I needed then D with respect to X, that answer column, negative 11, negative 5, and 82 would have replaced the X column. Would have had my original Z column. Rewrite the two columns, go evaluate. I wouldn't change the process at all. I would just change the initial setup of that particular matrix. So just to write that out. If I was asked or needed to find D sub X, then we would have these answers in the X column, original Y column, and now original Z column. Then evaluate that determinant by rewriting those first two columns and then going through that process again. But again, I just focused on finding Z on this. Gave us a couple of looks again at evaluating a 3x3 as well as working with Cramer's rule. All right, next thing we're going to look at will be an inverse. So our focus will be on an inverse of a 2x2 matrix. So let me get that up here. All right, an inverse of a 2x2 matrix. Now we can find an inverse, if an inverse exists, of any square matrix. All our focus is on right now would be the 2x2s. We need to do some more elaborate row operations and things for a 3x3, 4x4, things of that nature. But for what we're working on in this particular course, we're just focused on the 2x2. We have a formula for the inverse of a 2x2. So 2x2, which means 2 rows, 2 columns. Let's say the matrix is A, B, C, D. I'll just call it matrix A. Then that formula, this is a formula I need to make sure that I know. For the inverse would be 1 divided by the determinant of A. This is why we started this video with determinants. We had that Cramer's rule of the 2x2, so we had to do a determinant of the 2x2. I need it for this formula. Well, 1 divided by whatever that value is. And then the A and D switch places. And the B and C switch signs. So let's get an example up here. Let's say find the inverse. And we'll call this one A. Say it's 1, -5, 3, -14. So that's my original 2 by 2 matrix, A. I want to find A inverse. So A inverse would be 1 divided by the determinant of A. So the determinant value, we're going to go down. 1 times -14 minus, coming back, -5 times 3. So 1 times -14 minus -5 times 3. And all of that, 1 over that value, times, now let's get things switched around. All right. These two, A and D, switch places. So that would be a -14 and a 1. The other two elements switch signs. So it was originally a -5, switches signs, it's now a +5. Originally a 3, it's now a -3. So I need to go get this determinant value. Let's see, that would be -14 plus 15. That's just going to be a 1. Now, I will say this, it's not always going to be a nice 1, but 1 over 1's 1. We'll look at another one here in just a minute where I don't get a 1 down here. We'll see some fractions. In the original lesson video, you did get some fractions there. All right, so 1 over 1's 1. If I distribute the 1, then the inverse would be -14, 5, -3, 1. So that would be the inverse of that original matrix of 1, -5, 3, -14. All right, now we're going to put this inverse to use on a system of equations in just a minute. But the main thing I want to focus on, we're going to use in the system would be if I multiply an inverse by its original, I get the identity matrix. So let's kind of investigate that with this guy. So let's say here, I wanted to do A times A inverse. So A is 1, -5. I'm just copying from over there on the right. 3, -14. The inverse matrix was -14, 5, -3, 1. All right, if I multiply these two matrices, this will give us a little practice with multiplication from a previous lesson. It's row times column. All right, so that would be 1 times -14 plus -5 times 3. Excuse me, -5 times -3. And then 1 times 5 plus -5 times 1. I go to row 2. Let's see, 3 times -14 plus -14 times -3. And second row times second column, 3 times 5 plus -14 times 1. And if I evaluate each of those pieces, let's see, that would be negative 14 plus 15, that's 1. 5 plus negative 5, that's 0. 3 times negative 14 is what? Negative 42 plus 42, that's 0. And 15 minus 14 is 1. So we get this identity matrix. 1, 0, 0, 1. That's called the identity matrix because 1's going diagonally. The rest are zeros. It's actually, this particular one is actually referred to as I subscript 2. The subscript 2 just means 2 rows, 2 columns. It was a 2 by 2 one. But it is that identity. So important thing is 2 pieces. 1, I need to know this formula for finding the inverse of a 2 by 2. 2, I need to realize that if I multiply the original by its inverse, I will get the identity matrix. Now let's apply that in using an inverse to solve a system, a 2 by 2 system. All right, I now have a 2 by 2 system up here. The instructions are solved using an inverse. A little bit ago, we solved a 2 by 2 system using Cramer's rule. Now we're going to take a look at using inverses. I left my formula up there for my inverse. And what I kind of want to do is break this thing up. My original base matrix, again, would be the X column and the Y column. So I'm going to call that matrix A. Again, I can call it whatever I want. I'm just picking A. So let's see. 1, 3, 2, 1. There's that matrix A. And then I'm going to call matrix B the answer matrix. Negative 20, negative 5. That answer column. My focus is initially here getting the inverse of my 2 by 2. So I can't do an inverse of B, that's a 2 by 1. I need a square matrix. A is my 2 by 2. That's the one I'm going to find the inverse of, and we'll see why when we set it up here in just a minute, but I want that inverse of matrix A. So I'm going to go for that first. A inverse would be 1 divided by the determinant. Let's see, 1 times 1 minus 3 times 2 times. So these two switch places, they just are still 1s. That's not really changing anything. These two switch signs, which now they'll both be negative. All right, this determinant, that would be 1 over, that's a negative 5 now, 1 minus 6. And so we're going to be distributing that through that 2 by 2. So this would give me negative 1/5, positive 3/5. Let's see, positive 2/5, and negative 1/5. So now we're definitely seeing a more complicated looking inverse than in the last problem because I ended up with a fraction there for my scalar because that determinant wasn't 1 like it was last time. That's okay. I see more fractions and inverses than I don't see them. Okay? But there's my A inverse. So to use this to solve, what I'm going to do is I know that if I take A times A inverse, on the left side of an equation, then I need to multiply the inverse by the B matrix on the right side of the equation. So I have an equation here. It basically looks something like this. I've got A times our xy equals B. Answer matrix, original 2 by 2. Well, if this is an equation, then whatever I multiply by on the left, I have to do so on the right. So if I multiply the left side by A inverse, then I have to multiply the right side by A inverse. I can't do one side without doing the other. Now, what we just talked about was, if I multiply A inverse times A, I get 1, 0, 0, 1. I mean, I can go work it out, but I know I'm going to get 1, 0, 0, 1, that identity matrix. And so now if I look at this in equation format, I have 1x plus 0y, row by column. So that would just be 1x, 0x plus 1y. So that would just be 1y. Now let's look at what happens on the other side. This one I need to write out. Let's see, inverse negative 1/5. Just copying this from the left side over here. All my fractions. And then my B matrix would be 20, negative 5. All right. So I'm going to multiply row by column. So I've got negative 1/5 times 20. Negative 1/5 times 20 plus 3/5 times negative 5. Squeeze this in here. And then 2/5 times 20. Again, I'm doing row by column plus negative 1/5 times negative 5. All right, if I evaluate that, let's see, that would be negative 4 minus 3 is negative 7, top number. And then that would be 8 plus 1. That's 9. There's that bottom number. This is my x value. There's my y value solution. If I rewrite it, kind of all this together with just the numbers, we'll just move this up. So there's that identity. X, y equals, and my result I got when I multiplied over here, negative 7, 9. So that's telling me 1x equals negative 7, 1y equals 9. So x equals negative 7, y equals 9, or if I put it in an ordered pair format, negative 7, comma 9, or you could certainly write x equals negative 7, y equals 9. So solving by inverses, what I want to remember is I want to multiply the answer matrix by the inverse of that original 2 by 2. And when I write that, I always want the inverse on the left side. Okay? That goes back to our multiplying. So in this case, our inverse is a 2 by 2. So I have a 2 by 2 times my B matrix is a 2 by 1. So remember, I can do it because those insides are the same. It's going to give me a 2 by 1 answer. If I were to write the inverse on the other side, say I put the B matrix here, there's my inverse. I can't multiply them, so I've got to make sure that inverse is on the left side. And if you notice in my equation, I put the inverse on the left side on both sides. It really doesn't matter here because either way, it's a 2 by 2 times a 2 by 2, and it's going to give you that identity matrix, but it does matter on the right side because I can't do a 2 by 1 times a 2 by 2. I need to have a 2 by 2 times a 2 by 1. So when it comes to inverses, I need to know my inverse formula. I need to know that if I multiply an inverse by its original, I get the identity matrix, which just means ones diagonally, rest zeros. And if I'm solving using inverses, that means I need to multiply my answer matrix. In this case, it's a 2 by 2. That's all we're going to be worrying about in this course. At this point, I've got a 2 by 1 answer matrix by the 2 by 2 inverse of the original. Those two I'm multiplying, that will give me that solution for x and y. So inverse by answer matrix. Multiplying inverse by answer matrix would give me those solutions.